All right. Okay, I'm going to get things going here. I'm Dave Woon. I am the secretary of the astrochemistry subdivision. Joined today by our new vice chair, Chris Shingledecker here. Welcome to the subdivision leadership. This is an AstroCheminar sponsored by the subdivision and run by the grad students. And I'm going to turn things over to Kate in a moment, who will carry on from there. Um, just a couple of quick announcements. Two conferences, two symposia that be good to have on your radar. Next March, there will be a symposium that the subdivision is sponsoring, honoring Professor Eric Herbst. And Chris can tell you a lot about Eric since he worked for him. And that we expect the registration for that will be open in the next month or so for that meeting. Another meeting I'd like to draw your attention to is the International Symposium on Molecular Spectroscopy. And it's an annual event that's held at the University of Illinois every year. If you look for the website, look for ISMS. Next year, there's going to be a very big astrochemistry symposium run by Brett McGuire and some other people. That's a very broad treatment of astrochemistry. If you're not aware of the ISMS and have never attended one, it's sort of the biggest astrochemistry meeting of one of the biggest astrochemistry meetings of the year that doesn't have astrochemistry in the title. Anyway, with that, I will pass things off to Kate and turn myself off here.
Thanks, Dave. So I'm one of 4 graduate student organizers of these AstroCheminars, and we like to put on these events roughly every month so that we can showcase the current research in astrochemistry, especially of graduate students and early career professionals like Dr. Li. We also want to make sure that we have networking and knowledge exchange between various conferences, and of course, as Dave did, to advertise them when we do have such meetings. It's also relevant to share life experiences and broader career paths so that those of us that are young can learn about ways that we can pursue our careers. And so my name is Kate Gold. I'm a 4th-year graduate student in Lucy Zurich's lab at the University of Arizona. My work is mostly observational, studying the molecular content of evolved stars. Catherine, do you want to introduce yourself as well?
Yeah, so my name's Catherine Walker. I'm a 4th-year graduate student at the University of Wisconsin-Madison, working under Professor Susanna Wickes-Weaver. And I do a lot of lab-focused work, thinking about chemistry in the ISM, and rotational spectroscopy, gathering spectra for observational data. Athena?
Yeah, I'm Athena Flitt. I'm a 4th-year graduate student as well at the University of Mississippi, and I work under Dr. Ryan Fortenberry, and I do purely computational work. Most of that is either in reaction mechanisms, so construction of pathways and computation of rates, and also vibrational spectroscopy. And then Chisholm, if you want to introduce yourself.
My name is Chisholm, and I am a 4th-year PhD candidate at the University of California, Davis. I'm working on the Dr. Prep tree, and we do rotational spectroscopy of the torsional and exotic species spectroscopy.
Great. So we're really excited to bring this talk to you today. We have various talks, again, roughly every month throughout the academic year. We'll soon be posting information about our upcoming talks as well. If you have interest in giving a talk or interest in being an organizer, please feel free to email us. You can find that information on the astrochemistry subdivision of the ACS website, which we'll put in the chat before too long. The way that this will work is we'll spend most of the time with a really nice talk, and at the end, we'll also have a Q&A. So as you have questions, you can jot them down for later or enter them in the chat. We'll likely get to those questions at the end of the time. So with that, I'd like to introduce our speaker, Jialu Li, a postdoctoral associate at the University of Maryland, College Park. She studies the formation of massive protostars during their deep deeply embedded hot core phase from an observational perspective using high resolution spectroscopy in the mid-IR wavelengths and radio interferometer observations at sub-millimeter wavelengths. She earned her bachelor's degree in astronomy from the University of Science and Technology of China and her PhD from the University of Maryland. Her talk today is titled High Spectral Resolution MIR Spectroscopy, Unveiling the Intermode Structures of a Binary Hot Core. Thank you.
Okay, thank you for the introduction, Kate. So I think I can start to share my screen now. Okay, could you please tell me if you're looking at the screen normally?
Yes.
Okay. Okay, great. Thank you. So thank you very much for organizing this AstroCheminar, because while I have been using spectroscopy for a long time, it's actually the first time for me to really, think about how to tell the story from the perspective of astrochemistry, because from my own perspective in the past, I have been mostly focusing on, how can I use those spectroscopy to understand things such as structures or kinematics, so on and so forth. But I do feel that, when I'm preparing this talk, I do feel, it's indeed a very exciting story from the very first beginning of people's notice to hot core and to the follow-up studies we've conducted to it. So, in short, today, as we've seen the title, that our main role will be hot core, and I will present our knowledge or our studies toward it from mostly mid-infrared spectroscopy, but of course, the methodology is not only limited to this, and I hope I can kind of introduce the whole story in an interesting way, and hope you can share the journey that I have enjoyed. So in short, I think my own limited understanding to astrochemistry is actually really the pair of how physical activities and chemical processes influence each other. So I believe this is an image that we've seen in many places, which is about the life cycle of star, about how they form within dense molecular clouds, and how stars form, and how planets form on the disk, and then how such circulation returns back molecules back to the kind of empty universe. And specifically, along this circle, we can see that, different molecules, small or large, they form under different physical conditions. And of course, in the end, people who are working on this, we all care most about, in the end, how some of the molecules, they might bring traces of lives to our Earth or possibly to other places. And I must say that in this circle, this is possibly, from my perspective, not very complete, because in between the dense cloud phase and the accretion disk, the stars don't just appear. There's a stage that stars form when they're deeply embedded. And this is something I will introduce more about or define later on, the hot core or hot coronal. But in short, actually, I would say that people firstly notice those things was because, they see some jump of complex or simple organic molecules of their abundance. And now I'm going to turn to the first definition, or the first time that the name of hot core appeared in about 1980s, when people were focusing on the Orion molecular cloud. So at the time, as we can see in this spectrum, that a lot of interesting molecules appear. And at the time, the hot core itself, it's really something in parallel to some other structures defined for that region, such as compact ridge or plateau, things like that. But later on, people noticed that, for this kind of warm, compact things, actually is kind of representative. There are group of them actually associated with massive protostars. And in about 15 years, similar structures were found close to low mass systems, and those small things were defined as hot coronals. And you're welcome to ask me later on, because while the first hot coronal give the name to all the other hot cores later on, itself is not really the same hot core or I should say that for the most hot core we see later on. Anyway, so a short summary of their property is that they're compact, they're deeply embedded, they're dense, they're warm, and they have a very short lifetime. Though I need to emphasize that for this kind of 10 to the 5 years of short lifetime, it actually extends quite a long time for massive stars. It's about 1/10 of them. And I will show you more about what that indicates later on. Okay, but anyway, I've emphasized that it's the chemical part that really attract people's interest towards those hot core or hot corino. And so far, what do we learn about them? So first of thing is that people realize, okay, we should have some inheritance from the ice, because when we are looking at those hot core or hot corinos, we found several evidence. For example, there are a lot of abundant gas-phase water or methanol, or dominated by saturated organic species. And all of those indicate some hydrogenation process occurred on the grain surface. And also there is a high deuterium fracturation, because for this kind of chemical reactions, they're expected to occur in some rather cold environments. So when we notice that, okay, we see them in some very hot, or not hot, warm, several hundreds of Kelvin environments, we start to think about, okay, maybe it's because some ice sublimation release those molecules from the ice. And of course, the sublimation is due to the heating from the protostars within the system. And as the temperature rises, the ice sublimate and release those molecules. And follow up, there are some other chemical processes. For example, gas phase chemistry can make those rather simple organic molecules. They grow into some longer carbon chains, so on and so forth. And also shocks may also help to assist some of the reactions there. And the second thing is actually a spoiler here, because this is actually one of the conclusion, or I would say something we learned from mid-infrared spectroscopy, and I will talk more about how we draw this conclusion later on. But in short, this is another thing, how should I say it, another chemical property in hot core, which is that in those kind of high temperature environments, they really opened up some new chemical pathways and enable the formation of small molecules such as HCN, acetylene, and they can enhance their abundance by 2 orders magnitude. And so, okay, one thing I'd like to emphasize here is that for the two different passes, I'm really talking about a dichotomy in different energy regimes. And this is something really influence how we use our tools. So if we just think about, okay, we look at the system, looking through the dust, the cloud, and we see such a temperature gradient. And actually, so we know, okay, with all of those molecules in hand, how can we use them? So for rather cold energy, cold temperature, for a few to several tens of Kelvin, then actually they would we would see those transitions occur in millimeter or submillimeter. And for higher temperatures, we would see those low vibrational transitions, which because they correspond to higher energy, so we would see them in mid-infrared. So one thing I'd like to emphasize here is that really the tool we're using kind of really reflects the physical conditions there, and it's the properties of the cloud themselves allow us, okay, you can use this. This is the tool you can use. And so with those tools in hand, we can start to ask questions about, okay, where are these molecules? How they're excited, and what's their abundance, and how does the molecular inventory evolve? Okay, and so, but now with such an idea in mind, I'd like to just have a short revisit to the framework of star formation. As I've mentioned before, we have such a dichotomy of hot core and hot corino, and it's not simply that, okay, we give their name for fun, because there are actually intrinsic difference in between the two star forming process for those different systems. So, well, of course, we know that now we possibly have a rather good idea of how low mass star form, because I believe we've heard so much about, okay, class 0, class 1, class 2 systems, and a lot of exciting news about those things found in the evolution of disks or planets, so on and so forth. This is really because the star is born and with the visible disk, and a lot of those progress, they're just visible to us. And we can ask questions about, okay, how does planet form, or can we find the origin of life? But for high mass stars, this is a very different picture. I mean, it's not really a simple scaled up version of low mass systems. The one important thing is that the star is born because the hydrogen ignition starts very early. So the star is born while it's still deeply embedded. And so the radiation will be so strong that it may really hot the accretion process. So one of the essential questions for massive star formation is that, okay, how do those massive stars accumulate mass? Because if we just allow them to allow the strong radiation to do its work, then actually we cannot really see all the massive stars we see today. So this is really a very intrinsic problem, and that's why we have a different kind of questioning compared to low mass systems. And unfortunately, we don't really understand what's going on. As you see, I have covered a circle on top of this hot molecular core region. This is because, okay, we know that we see this kind of hot compact region with those abundant molecules, but those systems, they're very rare in numbers because they have a short life and massive stars are very little at the very beginning, and they're very far. They possibly form within very clustered environment and heavily obscured by dust. So it's really hard for us to really get as a comprehensive understanding as for low mass systems. So that's why now, okay, again, return back to our methods. We need to look for help from sublimeter or mid-infrared. So on the left, now I'm just showing an example of some of the properties of sublimeter because I'm going to do a comparison with mid-infrared observations very soon. So on the top, I have put just a figure illustrating, okay, how we see those CO pure rotational lines across different radio bands. So we can see that first is that, okay, they're nicely spaced, but also they're actually spaced rather distant. Or in other words, when we're doing such observation, we need to put different settings to do that. So in short, for those sublimeter observations, while they correspond to rather low energy regime, and we can get 3D data cube, and because those cool regions are somehow rather, I mean, extended compared to those very warm regions, we have this beam smearing effect, and we have to put different frequency settings on top of them. And also one of the very important reason is that for molecules such as methane or acetylene, they don't have dipole moments, so they don't really have pure rotational transition. So we cannot observe them in submeter or millimeter. And the nice atmosphere window, we know that's the advantage of radio astronomy. Okay, and as a comparison, now I'm showing the row vibrational transitions of CO just as an example. And so we can see that one very noticeable difference is that we can observe multiple lines simultaneously. And as for some of the other differences, we only have spectroscopy up to now. Maybe one day, hopefully, we can also get similar 3D data cube. And also, because of the size of the background, we're looking at some very warm regions. So it's really the small hundreds of AU continuum, mid-infrared continuum are providing the background. So which give us a very nice limit on the space, on the spatial region. And of course, now one advantage is that we can detect molecules without dipole moment. And so, okay, now I'd like to introduce how we do such observation, or what's our tool. So in this talk, I'm going to focusing on some of the telescopes we've used. So one is the IRTF in Hawaii, and also the SOFIA. They all work in mid-infrared, and SOFIA is not in space or in air now. It's in Tucson, in the Museum of Tucson. So that's a sad story. But when it was when it was conducting its tasks, it was able to fly above about 99% of water vapor on Earth. And so, as I've mentioned before, when radio astronomy, they have very nice atmosphere window. This is not really the case for mid-infrared. So that's why we need to put James Webb to the space. So for this figure I'm showing here, I'm showing two transition maps corresponding to what we will see if we are at the altitude of IRTF or SOFIA. So one thing in here is that IRTF works mostly on the left region of the dashed line, and SOFIA works on the right region. And those blue lines, they indicate, okay, how deep those pollutions from the atmosphere is. And when we look at those molecules, we realize, okay, those molecules who conduct a crime, they're basically those molecules who contribute to the greenhouse effect. And so, okay, it means that indeed, doing observations in mid-infrared is a challenge for us. But luckily, we do have Doppler shifts, which allows us to still detect the astronomical signals because for the astronomical objects we're interested at, they have some relative movement to the Earth. So that's why when we're looking at, so for example, some of the deep absorption of telluric lines in the bottom panel, which are indicated by the gray lines, we can see that, okay, as a comparison, we can see that, okay, there are some signals shifted to the left for those black spectrum. And this is, we can kind of think about in this way that, okay, for the same water line, the water line originates from the astronomical object, it's blue shifted, and so which are marked by all of those blue arrows. And if we divide the black and gray lines, we can see such a spectrum on the top panel, which show us nicely about, okay, those are indeed water lines from AFGL 2591, and those are not water from our own atmosphere. Okay, now we finally start to talk about the main role source, WSRS-5 for this talk, about how we did the mid-infrared absorption spectroscopy. So to give a very brief introduction of this source, it's a binary, very interesting, and massive binary. Both of them have kind of comparable mass, 20 solar mass, and they're separated by about 2,700 AU. And as we can see that if we're looking at this system from submillimeter, we would see a really large extended region of envelope surrounding this small continuum characterized by a few thousand AU. So this again justify us that while submillimeter is looking at a more extended region and might be suffering from beam dilution, for this mid-infrared, we're really having this small compact pencil beam as our background, and we're trying to understand something happened in front of this small 2,700 AU size. And as for this orange slit, this is, you can imagine that this is slit we put on it, and we can then get to spectrum for each source in the binary. And the next page, this is just because I'd like you to know, okay, how the spectrum look like. So, well, of course, we see that, oh, this is a very crowded spectrum. We have so many things. Well, it's very noticeable at about 4.7 microns that there is a valley, which indicates the CO ice. All of those crowded lines, they indicate gas phase CO. So I have put a zoomed in region on the lower right, and so we can see that they correspond to 12 CO, 13 CO, C18O. And if we compare it to the other binary, I'd like to just show it very quickly. So we can see that, okay, there are some different properties there. So once again, we need to thank the Doppler shift because it tells us that relative to the source itself, there are some velocity in between the structure who give rise to this absorption line and the source itself. And so that's how we continue our analysis, which is to convert those lines to the velocity space. Once again, use the Doppler shift. And in this page that, sorry, that seems that a lot of lines are lined here, but the basic idea is that for each panel here, I'm listing the transitions for different molecules, and I'm just taking a few of them as an example. And they're listed from bottom to the top based on their energy level. So we can see that, okay, for this red line, they're about 300 Kelvin, and we can see how the line look like for 12CO, 13CO, 18, and 12CO vibrational excited lines. And of course, we can immediately notice that we can try to link those different components at different velocity in between those different molecules, and then try to establish the connection. And one other information is that we, of course, can notice that different components, they behave differently when they're at different energy levels. And this tells us that, okay, they are characterized by different temperature and column density. So that's the key information to take, which is that, okay, we can decompose and understand their properties based on this set of lines, and that's fine. And one other thing is that other than CO, we also have Sophia observation focused on water. So on this page, I'm actually just copied part of the image from the previous slide and put water in parallel to just give you an idea about, okay, we can link different components from water or CO. And so we can know, okay, this component, what's the abundance of water in here and what's CO there. And I'd like to mention that for this source specifically, I only have water and the CO. That's because that's the data we have for WSRS5. But similar things can be done for molecules such as acetylene, HCN, NH3, CH4. And I will talk about some of them very soon. Okay, and now just that with so many lines in hand, I'd like to briefly introduce our methodology about how we analyze those lines. So in short, we use the Boltzmann relation, and which puts all of the tens or several hundreds of lines to convert their line profile to column density and put them in such a figure that correlates the energy level and column density. And we can read the temperature and column density based on the slope and the intercept on the figure. And this is an example of what we did for CO and water. But however, we noticed that this method can be problematic. And optically thin assumptions are not really appropriate. So which means that we cannot simply take what we see from the line strengths and convert that to the column, to how many molecules are within that column. So that's why we need to think about how to take care of that and interpret the column density properly. And basically by using analysis of curve of growth, basically we are trying to think about way that we can consider the saturation of the line profile when we have a large column density of molecules and the lines start to get saturated. And the standard way to do this is to think about, okay, we put a cold slab in front of the background continuum, and then we do the analysis of, we conduct, okay, all of the area, for example, of this absorption line to the right of the figure, which is the y-axis, and while the x-axis correspond to the line optical depths, we can determine by temperature and column density. So in short, we're converting all of our lines rather than in the rotation diagram in the previous slide. Now we're using curve of growth to do that interpretation. And basically it sounds like it's a standard way to do it. And when we use that method and put that back to all of our numbers of components in WSRS5, we can see that, okay, we can draw a conclusion. So in short, for this page, the information I'd like you to take away is that while I am presenting the average line of some low J and high J lines for all of those different molecules, but we can really use those colors to say that, okay, the same color, they represent the same physical, they have the same physical region, and we are sure that we are confirmed that by their velocity or temperature or column density. And so we can see that, okay, they might be linked to all of those different structures. So in another way, we put them in a sketch that the colors we see in the previous page, now we can put them in this figure. And once again, this is a conclusion based on kinematics, temperature, and column density. But however, while this sounds to be a kind of standard way in doing this or analysis absorption lines in the past, this is a reasonable methodology, but not the only one. So one key information I'd like to convey in this talk is that what we see really actually define how we should ask question. So to further illustrate this, I'd like to focus on this some of these, for example, cyan and purple structures on top of those dashed line, which indicate the velocity of the source itself, because they're abundant and they're hot. So actually in the past, in the era about 20 years ago, when people didn't have enough spectral resolution, those are the dominant components. And so I'd like to show you that how the spectrum look like observed by ISO 20 years ago. So in short, I have put the survey of many hot cores, one for water and one for acetylene and HCN, done by ISO. And one thing we noticed that, okay, we see all of those absorption lines everywhere. And well, we can use similar rotation diagram analysis because they were, I mean, those hot components dominate the line. So at the time, people find, okay, indeed, we only see those warm and abundant gas. But however, what this survey really, what questions really bring us is that one thing is that for low mass systems, those lines are not really seen in absorption, they were seen in emission. And the second thing is that when we compare the temperature of the dust or the gas, we found, okay, temperature of gas is kind of smaller than the continuum. And and also we have some questions from the abundance of HCN and acetylene, which I'll talk a little bit soon. But all of this in here brings us a question, which is that, okay, can we simply use a slab model to put it in front of the hot background and to do the interpretation? The answer is no, because for all of those points I've mentioned before, so they give very special requirements. So for example, for the ubiquitous absorption line, this means that, okay, for the survey for about the 20 sources in here, whenever we look at them, they always need to have some cloud, which is smaller than the continuum, no matter how the source is placed. And those small clouds must be along the line of sight. So this is actually a very restrict geometry constraint. And the second thing is that, okay, the emission and the absorption problem, this indicates that there must be some intrinsic difference between the two systems. And as for the temperature constraint, this is too coincidental. I mean, imagine for all of those 20 sources, we need to have such a constraint. This is, okay, this is a problem. And the first one, I'm going to show them in the next page. So this is something we learned from Sophia, and with the Sophia, and so the new observation, which can constrain the abundance in a better way. So in here on the right, I'm just showing again an average spectrum of all of those small molecules, such as acetylene, HCN, and H3CS, and they were derived to be about 600 Kelvin. And one important thing, or one important conclusion, is that for those molecular abundance, we found at 7 microns is about 10 times higher than those at 13 microns. So because those transitions, they originate from the same ground level. So we have the question about, okay, how to interpret this? This is not really some simple slab model can interpret. And so in Barr et al. 2020, a new, excuse me, a new model is proposed for the location of those hot absorbing gas, which is basically, as we've shown in this sketch, that we imagine all of those hot components originate from this kind of white bubble. And but Well, on the other side, we're looking at our continuum, for example, from 4 or 7 or 13 microns, because as the disk is getting larger, it's kind of getting cooler. So that's why 13 microns disk would have a larger spatial, it takes a larger space compared to the 7 microns. And that should be a way to kind of interpret, okay, the dilution of the abundance we see, because the abundance we derive is really from the gas relative to the continuum. And this model is great because it also answers some of our previous questions in the earlier pages. Because, for example, for this one, now we don't really need to have a slab model or have a foreground cloud in front of the disk with a very strong constraint about the geometry. And also it interprets about the size of different continuum at different wavelengths. And also the most important thing is that compared to disk in low mass systems, we know that we see those emission line is because basically the surface of disk is a kind of a PDR region. So there's strong radiation put there and we see those lines coming in emission. But on the other hand, for those massive systems, it's really that we have a warmer mid-plane, possibly due to viscosity, and the cooler space contributes to the absorption line. So this is a nice model which kind of explained all of our questions previously. And so then the method of how to analyze those lines is actually quite simple, because we can already take what we learned from stellar physics about analysis on the photosphere. And so it's kind of a similar curve of growth, and which introduce the line profiles. And so basically we're looking at some tau to the tau equals to the 1 region, and on the surface, the line the absorption line originated there. And so in conclusion, so while this set of figure kind of looks similar to what we have for slab model, this model works great for hot absorbing components because it avoids the strong constraints and provide a rather universal interpretation to the survey we have. So hopefully I hope that this can kind of justified, okay, what we see defined how we ask the question, because I think this is a really nice example in doing this. And we do have some efforts in trying to confirm the existence of the disk, for example, by trying to use, because we'd like to get image in short, and we can do that by, for example, observing some, okay, high energy lines in submillimeter, and this is a nice example for 2136 with the image from ALMA. But I need to emphasize that for those hot cores, those are really, we are still trying to confirm this case by case. And so while different methods have been applied to each of them. So for example, high energy water lines or HCN lines or some lasers, people are trying to do this one by one. So at this moment, we can still not conclusively say that, okay, this model works well for the mid-infrared and we can see the disk. No, the answer is still quite no. And we do have some efforts in trying to do that for WSRS5 itself, which is to, okay, once again, try to see if we can get some image in 3D, so we can also get the velocity information towards WSRS5. So we tried that with SMA, and for this figure I'm showing here, we can see that on the top left, we have the moment zero map, which basically tells us, okay, where are those, what was the structure of it, and some velocity structures indicated by the moment one map. And we even try to plot some PV diagrams, try to see if we can find any clues for the Keplerian rotation or things like that that might indicate the disk. But sadly, I'd say that we still don't have enough spatial resolution, so we can still not conclude that, okay, are we looking at some warped disk or just outflows in precision? Okay, so in this page up to now, I have really spent a lot of time in talking about what are the physical structures we can learn from the molecular lines. But as I've mentioned before, from the chemical perspective, one important thing we learned from absorption in mid-infrared is really that the chemical pathway opened under high temperature. So as I've shown before, we can see and estimate nicely the abundance of HCN or acetylene because now we can constrain them. Very nice. We have very high spectral resolution. And we found that they're enhanced by more than 2 orders of magnitude compared to those in dark cloud molecular clouds. So yeah, in here, I'm just trying to give you a recap and to show you that the high abundance reduced from those absorption spectrum. So this is interesting because people also notice this in hot core nodes I've mentioned, which are the sources related to low mass systems. And people, they have done such simulations, modelings for low mass systems. So in short, carbon and nitrogen, they need to release in atom form. And for such a chemical web, in a lot of places, the bottleneck is really the high temperature, but in the very warm, several hundreds Kelvin environments, those bottlenecks can be broken down, and such chemical paths can go through, and so which make us to be able to form those high abundance of HCN, acetylene, those so on and so forth. And I need to emphasize that such modeling were conducted actually based for PDR regions on the disk surface for small low mass systems called corinos. But we would like to take the idea also for hot cores, and one of the difference is that compared to having the UV from the source, which kind of liberate carbon and nitrogen, this task is replaced by cosmic rays in hot cores. And in Bar 2020, he had done an estimation about, okay, how cosmic rays can do this reasonably and allow such a similar pathways to happen. Okay, I know that we possibly have a very short time left, so I'd like to go through one more point very quickly to emphasize again about why nowadays we really need high spectral resolution of medium spectroscopy and how to make a difference. So in this page, I actually have copied one spectrum from the previous ISO I have shown before, and I have highlighted a few regions in this page, and each of them corresponds to each color on top. So we can really notice that high spectral resolution really makes difference because all the lines, they will be blended together. And not to mention that we can even decompose all of those different velocity structures and constrain their properties nicely. And this is something we do concern about, is because nowadays we have James Webb, which is very cool, of course, and working mid-infrared, and it doesn't have the annoying telluric lines. But the problem is that James Webb is also kind of doing spectroscopy with moderate spectral resolution. So in other words, it would have some similar effects. It won't be able to see all of those individual transitions as clearly as we have seen, for example, with RTF or with SOFIA. And so it will be it's worth to notice that, okay, we need to be careful when analyzing those data. And a short impression I'd like to leave to you is that if we have all of those lines blended, then one dangerous thing is that if we have a couple of different models, which is shown in this page, that so we can possibly think about, okay, the 3 spectrum on this page, they look very similar, but actually they have very different physical conditions. And so this is the problem, because for this spectrum I have here, they were generated based on James Webb's spectral resolution. So I hope this figure can just serve as some kind of warning that, okay, we need to do that carefully, because otherwise we might have incorrect estimation. Well, and the key problem in here is that really optically thin lines that reflect the actual column density, they're ignored. So that's why if we just want to simply do a comparison in between the spectrum and our model, we tend to ignore the weak and thin lines and give wrong estimation. So just as a advertisement of our work in analyzing the problem in the paper, Li et al. 2024, we developed a tool to kind of help you generate absorption spectrum. So you can do that yourself and see how you can determine that model in a nice way. Okay, here we come to the summary page. Do we have enough time, or I should just leave it here? Well, I guess I can just go through it very quickly. That I hope, well, today I've emphasized that how we can know about the kinematics, or we can constrain temperature and column density of individual velocity components by high spectral resolution mid-infrared spectroscopy. On the other hand, we are really having a very important lesson that we learned, which is that, okay, what we saw defined on the question we need to ask. So while the SLAP model to interpret absorption lines seem to be a standard and easy way, but what we see when putting all of those evidence together, we realize that, okay, we do need some other models to do the interpretation. And the third thing is that in such high temperature environments, new chemical pathways were opened in hot cores. And in the end, that high spectral resolution is great. And I look forward to EELT and those big telescopes very much, and see, I mean, it would be great that one day we can also have 3D data cube for mid-infrared. Thank you for, yeah, that's it. Thank you for your patience and your interest.
Thank you, Dr. Li, for your talk. We do have plenty of time for questions, and so please enter questions in the chat. I see a few questions from Emma Pelerin. The first question, why was the Doppler shift analysis used on water specifically? Is this technique useful for other chemicals that are present in both systems?
Oh, okay. I also see the next message saying that it was answered. But basically, yeah, this is the same idea, no matter whether it's for water or other molecules, because of course we know that we have caloric absorptions for other molecules, such as methane in our atmosphere, the same. But if you're interested in about CH4 from the hot core, their velocity component would also be, I mean, shifted due to the Doppler shift, and we can retrieve that signal from the spectrum.
Jialu, I'll ask a question. You talked about the resolution issue of JWST at the end of your talk.
Mm-hmm.
Just as a general sense of appraisal, there's been a lot of JWST information about exoplanets, about ices, about various things. How much do we trust all that stuff?
I think, well, of course, as I've mentioned before, that this kind of chi-square methods when people were trying to interpret the spectrum by comparing this model and the observed spectrum. Well, this was usually conducted for most of such analysis, which I had questions about. But recently, I do notice that people cited this paper and this paper in emphasizing this problem, and they start to would mention, okay, we should really focus on those optically thin lines, and if we only focus on those optically thin lines, what would the difference between the models? Would be the difference of the results we derived by comparing just simply to all of those lines. So, for example, I saw this example in one of the Joyce survey, which conducted for low mass systems, if that answers your question.
Yeah, it very much does. Thank you very much.
We have another question from Curtis DeWitt. Can you say more about the Orion hot core? Is it like W3 IRS5?
Thank you for asking this, because I mentioned this very early in this talk about, okay, even if we got the name of hot core from that source, it's not really similar to the other hot core we've been talking about later on. This is because for that first hot core, it's actually something externally radiated by the protostar. So as a comparison, for almost all the hot cores I've been talking about in this talk, we have a protostar embedded in the system. And so for all of the materials we see, they're kind of internally heated rather than externally heated. So I think that's a very interesting history.
Thanks for that. Do we have any other questions anyone would like to drop into Q&A?
If anyone would like to ask a live question, I think it's possible if you raise your hand, I could actually let you talk out loud. If anybody has a more complicated question, perhaps. I don't see any hands going up.
Somebody else did drop another question in the Q&A though. You had mentioned the difficulty in identifying acetylene concentrations due to a lack of a dipole moment, I believe. Could the methods developed be used to identify other molecules without dipole moments that may not be in the gas phase? So I assume as ices or dust grains in general.
So they'll be thinking about those bounds kind of for those solid phase. Then we're then talking about looking for ice in mid-infrared. If that kind of, well, I mean, I'm also reading about this question. So so I think I would like to first, to talk about the first sentence about identifying acetylene is hard. I mean, it indeed doesn't have dipole moment, but it doesn't mean that we cannot observe its other spectroscopy properties. So that's why we can still see them, identify them in mid-infrared. We cannot see them in sub-millimeter or millimeter as for molecules such as CO, because they have dipole moment. But we can use raw vibrational lines of acetylene and do measure them at mid-infrared. And so that's basically the advantage of doing those in mid-infrared. And they also have, for example, in solid phase, they have those ice properties. Once again, at mid-infrared, we can observe them. If that answers the question.
Thank you, Dr. Lee, for your answer. I think it also would be plausible that we could use a quantity like the dipole moment derivative for these things. I do want to spend a moment as we wait to see if there's any other questions to advertise some of our upcoming events. Athena, do you happen to have those handy?
Yeah, we have currently 3 more talks scheduled through February. So next month, December 10th, we're going to have Martin Cordner from NASA Goddard come and speak to us. And then after the new year, Karin Oberge from the CFA is coming to talk to us on January 22nd. And then in February, our AstroCheminar is going to be with Jordi Bowman from the University of Colorado Boulder, and that's February 17th. And so if you have any ideas for anybody who might want to speak after that, we would love to hear your suggestions.
Okay, I think if there's no more questions, I want to thank you again, Jiayu, for your talk today. And we will be looking forward to seeing everyone at the next AstroCheminar.
Okay, I am going to wrap things up. Thanks for showing up, everybody. Have a good afternoon or whatever. Bye.
Thanks for joining. Bye.
Bye. Bye.
Thanks again for organizing this.